Okay, let's begin. We're filming. Now, this is one of the more complex problems that you're going to have to do in this unit. And it is an example problem, so it's well worked out completely. So it's a great way to begin. There's some here, Zach. It's a great way to begin a discussion of this material because it's such a well worked out problem that I want you to ask questions, okay? Now, it says, I'm going to read the problem to you twice, okay? Example 10. So let's write that down. Example 10, not exercise 10, example 10. And that's problem set 11, okay? It says to cool her 0.200 kilogram cup of 75-degree Celsius hot chocolate, mostly water. Somebody calculate for me what is the temperature of 75 degrees? 75 degrees. So 75 degrees Celsius times 1.8 plus 32. 75 times 1.8. What is it?
167.
167. So 167 degrees Fahrenheit. So it's pretty hot, would you say? Okay, it's pretty hot. All right. It says to cool her 0.2 kilogram cup of 75 degrees Celsius hot chocolate, mostly water, Heidi drops a 0.03 kilogram ice cube at 0 degrees Celsius into her insulated foam cup. What is the temperature of the hot chocolate after all the ice has melted? Now, this is significant. There are two things that I want you to understand here. The first is a term which we learned last unit, and that was adiabatic. Adiabatic, it's actually Greek meaning fortress, meaning impassable. An impassable fortress would be adiabatic. Okay, so something that's impassable. Clear? Adiabatic. So heat is neither entering nor leaving. So I have a styrofoam cup, insulated. The styrofoam cup tends to be adiabatic. Clear? First word? Okay. Secondly is you can have ice at negative 20 degrees Celsius. You can have ice at negative 100 degrees Celsius. Okay? However, the ice here is actually 0 degrees Celsius solid. That's important. It's 0 degrees Celsius solid. And we're going to have to melt that to 0 degree liquid. Now, you're looking at me like, no big deal, but that is the essence of this problem. Clear? Yes? The hot chocolate is going to lose energy. Correct? The ice cube is going to gain energy. It's going to melt, and then that water that made up the ice cube is then going to warm up. Correct? At the same time, the hot chocolate is losing energy. Correct? Are you okay with that? Okay. So, let's begin. Let's read it again. To cool her 0.200 kilogram cup of 75 degrees Celsius hot chocolate, which is mostly water, Heidi drops a 0.03 kilogram ice cube at 0 degrees Celsius into her insulated foam cup. What is the temperature of the hot chocolate after all the ice has melted? Okay. Well, first thing I want to do is I want to write down what I have. Is that easy? I want to write down what I have. So, I have the mass of the hot chocolate. What's the mass of the hot chocolate? Mass of the hot chocolate.
0.200.
0.2 kilograms. Now, what's 0.2 kilograms? Do you have a visual on what that is? All right, 1 kilogram would be a liter. 1 kilogram would be a liter. So this is 0.2. This would be, this is 500 milliliters. This is a half a kilogram, about a pound-ish, right? So this is 500 milliliters, which is 500 kilograms-ish, assuming the density of water is 1, and this is a little bit less than the density, or a little bit more than the density, whatever the case may be. Okay, this would actually float on water. Okay, could you shut the door, please, so we have some privacy? Okay, now, so what is the mass of the ice? Are you done, Katie? It's right there? Okay, thanks. What's the mass of the ice? 0.03 kilograms. Correct? All right. What is the heat of fusion? Now, it's given in this problem. What is the heat of fusion? Heat of fusion. The heat of fusion is the energy required to change a solid into a liquid without a change in temperature. So 0 degree ice into 0 degree water. I'm saying water, liquid water. So solid water to liquid water. Clear? That's the heat of fusion. Okay? We say that's H sub F. We call it heat of fusion. And Zach?
3.35 times 10 to the 5th.
3.35 times 10 to the 5th. Let's just write that out instead of using scientific notation. It's just a little bit more understandable when you just write it out. You can see it more conceptually. So that would be 335,000 joules per kilogram. Correct? Yes? Okay. What is the specific heat capacity of water in joules per kilogram? 4,187 what? Joules per kilogram degrees Celsius. Yes? Now, if I said what is it in kilojoules per kilogram, it would be 4.187, right? Yeah. Yes? So you got to make sure. What would it be in calories? How many calories per kilogram degrees Celsius? Would be 1,000.
Yeah, so it'd be 4.1.
Instead of 4,187, it would be 1,000.
Oh, just 1,000?
Yeah, 1,000 even. Even. Okay? That's the specific heat capacity of liquid water in calories per kilogram is 1,000 calories per kilogram degrees Celsius. Understood? Now, what else? What is the temperature? Is this coming out? Can you see this?
Yeah.
Yep.
Can you see it? How far down can I go?
A little bit further.
Can I go? Should I go up here?
Yeah.
0 degrees Celsius. That's the initial temperature of the ice, correct? Yes? And then, what's the initial temperature of the liquid water? Can we call liquid water just water
Yeah.
for point of the problem? Is that okay? Okay. So,
75.
75 degrees Celsius. Are we all set with that? Now, what equation are we actually going to be using here in order to solve this? What equation are we actually going to be using here?
Heat loss equals heat gain.
Heat lost equals negative heat gain. Now, what the book is doing, the book is saying, okay, heat lost equals heat gained, and then they're switching the delta T to Ti minus Tf. They're kind of cheating a little bit, but that's wrong. That's mathematically incorrect. This is the correct way of doing it. Clear? The book is wrong. Understood? All right, now, what's losing the heat? What's losing the heat?
Hot chocolate.
The hot chocolate, right? So the mass times TF minus what? What's TI? Well, let's not do that yet. And this is just of the water, right? Right? C of the water, yes? Yes? Okay. What's that going to equal?
Math.
What's going to be the heat gained? How am I going to find the heat gained?
Math.
What's the heat gained? What's gaining heat?
Ice.
The ice cube. Okay, now, the ice cube is going through two heat changes. The first heat change is to melt the ice cube. You get that? The first heat change is to melt the ice cube. So, how do I know how much heat is being consumed by the ice cube from the hot chocolate in order to just change the ice cube from 0 degree solid to 0 degree liquid? What did I say that was? I said that was heat of fusion, right? So it'll be the mass times heat of fusion. Isn't that correct? And that will tell you how much heat is needed just to melt it. Now we're at 0 degree liquid water, correct? Now we're at 0 degree liquid water, yes? And you want to, are you adding or subtracting that value? Are you adding or subtracting the heat needed to change the ice cube from 0 degree liquid to some final temperature? You're going to add it, okay? So you're going to say plus, is this, can you see this? You're saying plus the mass of the ice cube, TF minus TI.
Can't see it.
You'll be able to. It's a little bit of a correction. I'll move it over a little bit. Yeah, it's still, you can still see it, but I'll move it over anyway. Okay. So that's going to change. So that's going to be, this is going to be of water, right? The same value that's over here. You see that? I'm going to erase everything. Can you keep your wits about you and remember what the various values are?
Yeah.
You have that right in front of you, so, okay, all right. And I want you to be able to verify the calculation, so you need your calculators out. Okay, so I can erase all this, yes? Okay, good. All right, now, right, let's just rewrite the equation that I wrote that we're going to actually plug into. It's actually becoming very easy, I think, all right? So it's the mass of the hot chocolate. We'll say HC for hot chocolate, right? You know what, we're not gonna put hot chocolate, I know what to do. This is gonna be hot chocolate. Okay, and it's gonna be mass equals, right, equals, this is the ice side, the mass times heat of fusion, right, plus the mass of the ice cube, TF minus TI, water. Yes? Are you with me?
Yes.
All right. So what's the mass of the hot chocolate? It's going to be 0.2. I'm going to leave off the unit labels. You just want to make sure. Wait a second. Do yourself a check. What's mass in? Kilograms, check. What is temperature in?
Degrees Celsius.
Degrees Celsius, check. What is heat in? Joules, excellent. What is heat of fusion in? Joules per kilogram, correct? And what is specific heat capacity in? joules per kilogram degree Celsius. Do all the unit labels check?
Yeah.
Yes, so now we can leave off the labels and we'll stick it on at the end, okay? Yes? Okay, so point 2, TF minus TI, we know that. TI is what?
75.
75, and that's the specific heat capacity, 4187, right? Equals, the mass of the ice is what, 0.03?
0.03.
Is that correct?
Yeah.
And then TF minus what?
Heat fused.
What's TI?
Oh. Wait, you
Yeah,
didn't,
0.
Well, we don't need that, do we? We don't need that, do we?
you didn't.
Because there's no temperature change when you talk about the heat of fusion. It's just mass times the heat of fusion. You see that?
So it needs 33,000.
It would be, it'll be 0.03 times 335,000. Isn't that correct?
Yeah.
Right? 335,000, isn't that what we said before?
Yes.
Okay, all right. Plus 0.03. 0.03, right? You with me?
Yes.
Okay. Times TF minus what? 0. And what is the specific heat capacity of water? 4,187. I have a wonderful period 9 today. I usually introduce my period 9. Judine, a frequent visitor. We have Warwick. Hasn't been as frequent lately. Okay, very good. Carly, not Ann. Carly, not Ann. Jackie is becoming more of a frequent visitor, and Bree, kind of like guest appearance of Bree. She's kind of like making a cameo of her crazy self from period 2. Excellent. We like to see Bree after school. Excellent. Now, so now let's get rid of some of this stuff, okay? I need you to help me out here. So what's 0.2 times 4,187?
837.4.
837.4 TF minus 75. So far so good, is that all right? Cool, are we there? Okay, what is 0.03 times 335,000? 10,050?
Yeah.
Okay, so it'd be 10,000, is that correct?
Yeah.
10,050, okay, plus 0.03 times 4,187. 0.03 times 4,187 is what?
125.61.
125.6 is fine. 125.6,
Yeah.
okay, and then it's going to be TF
Minus 0.
minus 0, okay? Looking good here, guys, looking good. Okay, let's distribute this here. Let's distribute 837.4 through. Okay? Can we do that? Okay? So that's 837.4 TF, correct? Yes?
Yes.
Minus
62,805.
62,800.
5.
805. Okay, equals. Now, I purposely left something out to see if you caught it. What was that I left out? What was it that I left out?
Oh, yeah, you forgot the 4,100.
No.
Oh, no, you didn't. Just kidding.
The negative. The negative, correct?
Yes.
Yeah? You gotta make sure that you honor the negative. You have to make sure that that is there. Otherwise, you'll get a number that's lower than it should be. number should be 50. It'll be less than the lower value. So do you see how the answer has to be between 0 degrees, the ice, and 75 degrees, the hot chocolate? It's going to be somewhere between there.
Yeah.
If you didn't put the negative sign, your value is going to be less than 0. It usually becomes less than the lower value if you don't put in that negative. Okay? So you got to make sure that the negative is in here. Right? So negative. Right? So this is going to be 10, 0, 5, 0. Right? Plus 125.6 TF. So you see how that drops off? That 0 drops off? So now let's rewrite this. This is, what is this here? This is 6,000?
Yeah, wait, it's 62.
837.4 times 75?
Yeah, 62,000.
62,805. Okay, now let's just read what we have to make sure we know what we're doing. 837.4 TF minus 62,805 equals negative the value 10,050 plus, that plus? Yeah, that plus this.
Yeah.
Okay? Are we set with that so far?
Yeah.
Okay? So now, we're running out of room here very quickly. Alright? So let me get rid of this. Okay? Let's rewrite this up top, but we're going to distribute that negative sign. So we're going to conserve as much space as we can, okay? So this is going to be 837.4 TF minus 62,805 equals negative 10,050 plus, sorry, that's negative 125.6.
Yeah.
Correct?
Yeah.
Is that right?
Yeah.
Yes? Okay, now, I want you to bring this over here, okay? And I want you to bring this over there. All right? Yes? Can you do that? So, here you have 873.4 TF plus 125.6. So what is 873.4 plus 125.6?
960.
What is it?
999.
999?
I did not get that. I got 960.
Yeah, 999.
999. Okay. So this is 999 TF.